Good afternoon. I think I am the last one. I am Emre Gençer. I am the co-founder and CEO of Sesame Sustainability. And today I will be speaking about our project with Newlab on supporting their Louisiana hub. So this particular project that we are doing is systems modeling for scalable direct air capture technologies. And before I start talking about the project, I want to also briefly introduce Sesame, what we do, and briefly our story. So Sesame is a software company. So we started Sesame like 2 years ago. It's a MIT spin-off. And before starting Sesame, I was a research professor at MIT. And we actually started building this software in 2017. And currently we have very large customers like Chevron, JERA, actually using Sesame for their decision making on energy transition. And the focus of our platform is how can you make better decisions in your decarbonization journey. So it's a strategic planning software to be able to identify the right pathways for you to achieve your emission reduction targets. And our target industries are basically hard-to-abate sectors, oil and gas, utilities, steel, so on and so forth. So the secret sauce that we have is basically we believe that to understand energy transition and decarbonization journey, you really need to bring together different modeling capabilities. And these are cost modeling, emissions modeling, power system, which is basically a detailed system modeling, and also including policy levers, so on and so forth. And all of these are, of course, necessary components, but also hard-to-abate sectors, especially industry, require bespoke solutions. You cannot just go to a refinery and say, reduce your emissions by 90%. You really need to be able to tell how they can achieve that, whether it will be changing their heat source or electrification, if they are doing electrification, in what sub-processes, so on and so forth. And in Sesame, we brought together all these modeling capabilities into a single platform. And also, we built a relatively easy-to-use user interface. So actually, the expertise you need to be able to run scenarios is significantly lower than a traditional way of doing these kind of analysis. And in this direct air capture hub component, basically, that we are currently working on, it is a similar problem for us, right? So this is a systems problem because, like, even though we are talking about direct air capture, it doesn't end there, right? So if you think about a very simplified characterization, so like at the center we have direct air capture technologies. First of all, we have multiple direct air capture technologies. Each one requires different things, like it can be power-based or thermal-based. And once we capture CO2, the story doesn't end there because then we need to decide on the destiny of CO2, whether it will be sequestered or converted into other products. And if we are converting into other products, it can be fuels, chemicals, or other materials. So as you can see, so even though we are talking about direct air capture as a one single technology, when you think about the deployment of this technology, there are so many decisions we need to make. And we are helping Newlab basically doing this modeling to understand both the technologies and cost and emissions analysis of these technologies, as well as the rest of the value chain. And I just want to show you one particular technology and how we are modeling this. So like relatively, like I picked one of these basically, and I'm not sharing any names of the stars, and I don't know whether I am allowed to, but I am not sharing. So basically, as you can see, so this is our kind of platform. So I would say basically we built almost like SimCity for industrial decarbonization. So we have these building blocks that are ready to be used, and then you can connect these to represent your value chain. And here we are representing one of the DAC technologies, and then we are using this basically to be able to run scenarios. And actually, it was in one of the earlier panels. I really liked it. So basically, you can make mistakes in the digital world rather than real world. And basically, like this is the exact approach we are taking. So try this, pressure test, different assumptions, understand how this can work, and then ultimately deploy at that scale. So I will show you two examples. One is scale. So as we've also heard in the previous panel, scale is very important, and until we achieve scale, actually most of the technologies are prohibitively expensive. Same thing for direct air capture technologies. So let's say if we have, okay, I should have numbers here, but so if we are capturing 100,000 tons per year, then this technology will cost around $575 per ton of CO2 captured. It's extremely expensive. And when we increase the scale to 1 million tons of CO2 capture per year, actually you can reduce it to less than $200. And if you look at these, basically the green parts that you are seeing are the CapEx, like the capital deployment. And mostly with the economies of scale and also learning how to do these technologies, you can significantly reduce your unit economics. And also you can see here we have the blue bars, which are the taxes and credits, which is 45Q basically. And still the like government subsidies plays a huge role here, as you can see in the overall economics of these technologies. And I will show you another quick example. And we are not only doing the cost analysis, because believe it or not, even direct air capture comes with environmental impact. Because in some technologies, you need to use natural gas, so for thermal purposes. Or your power system might not be 100% clean. So we assume for this case that actually it is 100% clean, and we are supporting like the natural gas supply with renewable natural gas. But even in that case, you need to really understand where is the sweet spot. So how much renewable natural gas this technology really requires to be blended with conventional natural gas to be able to hit zero emission. And in this case, basically, our modeling shows that for this particular technology, around 15% you need RNG to really have a net zero direct air capture technology. And of course, this comes with a cost penalty, not surprisingly. As we increase the RNG, we see that these technologies are getting slightly more expensive. But again, so before we deploy, before we make all these decisions, we need to understand all these things that can change and that we kind of have control over. And I will end here. So basically, like with DAC or any other emerging technologies or decarbonization of conventional technologies, we need system scale modeling to understand all of these and making these mistakes in a digital platform. So with that, I will end my talk, and thank you very much. And thank you very much for sticking around.